All right, my friends, let's take a look at the first problem here. I'll definitely say at a glance, it looks pretty scary, but if you just break it into little pieces, not a bad problem at all. So it's got the table here at T minutes is giving you degrees Fahrenheit of the water. It says the temperature of water in a tub at time T is modeled by a strictly increasing twice differentiable function, W, where WT is measured in degrees Fahrenheit and T is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. Values of Wt are selected at times t. For the first 20 minutes are given in the table above. For part A, it asks you to use the data in the table to estimate W prime of 12 and to show the computations, lead your answer using correct units, interpret the meaning of your answer in the context of this problem. I will always give the same advice for anything with tables like this one. If you struggle at any moment, I say just go ahead and sketch out a graph of the function. Your sketch does not need to win any awards. Honestly, like everybody else can just butt out as far as their opinion, because really it's just something that helps you figure out what's happening here. So I'm just going to go ahead and mark the t-values. Notice they are uneven, so they go from 0 to 4 and then to 9, jumping up then by 6 to 15, and then jumping up by 5 to 20. All right, and then the outputs, I'm just going to make that ziggy-zaggy there. I'm going to make these be increments of 5. Okay, and then I'm just going to plot the points. So at 0, it's 55. At 4, it's 57.1. I'm just going to go ahead and label that's 57.1. At 9, you've got 61.8. 15 goes in, 67.9 comes out. 20 goes in, 71 comes out. There we go. And it said that there's some, increasing twice differentiable function connecting it. So who knows? It probably looks something like that. So here's a graph. Now we're reading part A. Use the data in the table to estimate W prime of 12. Well, 12 is smack in the middle of 9 and 15. And so W prime, we all know, means the slope of the tangent line, which would maybe look like that. I don't know, since I don't know exactly what the function looks like. But I hope it makes sense if you grab the data points on either side and do the slope of that secant line between those 2 points, that you probably have something pretty close to the slope of the tangent line at 12. And that's what I'd recommend for part A. So just say W prime of 12 is approximately, and you're just going to do 67.9 minus 61.8 over 15 minus 9. And this is a calculator problem, so you could just turn that into a decimal, or you could be nerdy like me and, just subtract stuff. Anyway, I got W prime of 12 is approximately 61 over 60, which of course is the same as like 1 and 1/60th. And then I just said degrees Celsius per minute. Now they wanted you to interpret what this means in context to the problem, including correct units. And so let's see, I think I'll go this way. And this means that the temperature of the water at time t equals 12, and let's put units on there. So 12 what? 12 minutes. The temperature of the water is increasing since it's positive at a rate of approximately, I'll just say 61 over 60 degrees Fahrenheit per minute. There we go. All right, so that's part A. Okay, now for part B, use the data in the table to evaluate, to evaluate the integral from 0 to 20 of w prime dt. Using correct units, interpret the meaning of that integral in context of the problem. Okay, so part B, first thing I would recommend after copying that piece right there, that integral, would be to use the fundamental theorem of calculus. So the antiderivative of w prime would be w, and then if you plug the bounds in, this would simply be w of 20 minus w of 0. Hopefully that makes sense. And then if you look at the table, or your graph for that matter, w of 20 is 71 and w of 0 is 55. And so now, if you're not sure how to put units on there, you could just ask yourself 71 what? And it would be 71 degrees Fahrenheit. You wouldn't have to put this here, but you could. And then minus 55 degrees Fahrenheit. And then subtract that, and you end up with 16 degrees Fahrenheit, or 16. So, so for the part where they asked you to just, what does it say? Evaluate the integral, just saying 16 is totally fine. So you wouldn't especially have to have the degrees Fahrenheit on there. Okay, so we got the 16 there, but now let's interpret it in context of the problem. So the integral from 0 to 20 of w prime of t dt is, and I do a very literal translation of things like this. I don't really add much warmth to it. So I would just say it is the difference. I just do the really literal translations in the water temperature or temperatures at time t equals 0 minutes and t equals 20 minutes. There you go. There you go. Is the difference in the water temperature? You could also, let's see, difference in the water temperatures. I should add this in degrees Fahrenheit. I should add that in. Now let me reread it, make sure I got it. Interpret the meaning. Yep, got it. Okay, and then I'm just going to go ahead and add 16 degrees Fahrenheit back there just because I feel a little paranoid. Okay, anyway, hopefully that makes sense. You could also say that that's how much the temperature of the water warmed up by. There are different ways to word that. Now moving on to part C, it says for t values between 0 and 20, the average temperature of the water in the tub can be found by taking 1 over 20, multiplying it by the integral from 0 to 20 of wt dt. First of all, I hope you do recognize that as something that you could have come up with instead of them giving it to you, because they do not always give that to you. So just recognize that as average value of a function. You have a flashcard for that. They want you to use a left Riemann sum with 4 subintervals indicated by the data in the table to approximate that average temperature. And then they want to know, does this approximation overestimate or underestimate the average temperature of the water over those 20 minutes? And they want you to explain your reasoning. So I'm going to come back to the picture for this. So for part C, and since you drew the picture, you're ready to go. I'm going to erase those little tangent lines off because we don't really need them. So you've got some function here. And the idea is, let's just kind of think about the value of the integral. So from 0 to 20 of w of t dt. Let's just worry about that. It does have a 1/20th in front, but let's worry about that for a second. So that would be the area under the curve, adding up all those temperatures from 0 to 20. But we are not going to get exactly that area. We're going to use a left Riemann sum. And so the subintervals as indicated by the table would be 0 to 4, 4 to 9, 9 to 15, and 15 to 20. A left Riemann sum is where you just use the height on the left of each rectangle and calculate the area. So I would say this is approximately, the first rectangle has a base of 4, and then you multiply it by the height, which would be 55. The second rectangle has a base of 5, and the height would be 57.1. The third rectangle here has a base of 6, You're multiplying it by 61.8 for the height. And the fourth rectangle has a base of 5, and you are multiplying it by height of 67.9. But that's just the value of the integral. And so if you're multiplying by 1 over 20, it would be like multiplying the entire right side by 1 over 20, or just dividing the whole thing by 20, either way. And so, it's a calculator section. So you just calculator all that up. And I believe you get that 1 over 20 times the integral from 0 to 20 of WT dt would be approximately 60.79. I think there's a 0 after that, degrees Fahrenheit. And so, or no, that's exactly what we got, but it's an approximation. That's what it was. Okay. Anyway, so then they wanted to know, is this an over approximation or an under approximation? If you look at the picture, you can see that it is definitely an under approximation. So I'm going to start by declaring that. So this is an under approximation. Now, how come? I would say because, and this is some language you might want to just put in your back pocket, because they said that the function's increasing, and we used a left sum, and I would just say it that way. So we used a left sum on an increasing function. There we go. Hopefully that makes sense, my friends. All right, moving on to part D. And I'm running out of room here. Okay, part D says, for t values between 20 and 25, I'm going to circle that so you don't mess up like I did. Doesn't say 0 to 25. It says 20 to 25. For the function w that models the water temperature, has a first derivative given by w prime of t equaling this mess. Based on the model, what's the temperature of the water at time t equals 25? Okay, so I hope it makes sense. What we want is w of 25, but we have w prime. I hope it's not a surprise that an integral with respect to t will be part of your solution. And then we're going to use 20 and 25 for the bounds, and just be careful how we interpret it. So for part D, I hope this makes sense. The integral from 20 to 25 of w prime of t dt, if you just think about antiderivative of w prime, it's w and then plugging in your bounds. So you'd have w of 25 minus w of 20. Now the integral on the left is something that I would make my calculator do, just using the numerical integration function. And we would end up with something approximately equal to 2.043 with that integral on the left side. Now, the temperature at 25 minutes is what we're trying to find, but you can go to the table or your graph and figure out what the temperature was at 20 minutes. You could put 71 in. So that's what I'll do. So minus 71. One more move, just add the 71 over. And 71 plus 2.043 would be 73.043. And then they wanted to know the temperature at that time, and so I would say degrees Fahrenheit. There you go. All right, my friends, hope that makes sense. Take care, everybody.